Welcome to AI-driven perception, learning and mapping for drones. Previous lecture we talked about foundations of convolution neural networks and various aspects of operations, convolution operations and learning and applications, right? This particular module focus on recurrent neural network. We'll look at how we learn from sequential data, particularly we look at a feedback neural networks. Specifically shallow neural network, which is what we call memory neuron networks, and its applications for system identifications of drone. So this particular lecture focuses on sequential data with the feedback neural networks, understand temporal data, understand sequence modeling, right? Different type of feedback neural networks. What is a feedback? What are the issues associated with the feedback neural networks? One such neural network is memory neural network, and how learning algorithms for a specific memory neural networks we will discuss in this particular lecture. Finally, we talk about how to use the recurrent neural network for system identification of the drone. Right. What's a sequential data? Right. See, you need to understand the difference between temporal dependencies and data which doesn't have a temporal dependency, right? So sequential data is where the order of element carries a meaning, right? For example, if you're talking about aircraft, or if you're talking about a drone system, you are giving a input to thrust, right? You are increasing the throttle and you are expecting the aircraft to climb, right? It climb at a specific rate, and you bring back the throttle, it hover at that particular point. If you are pitching forward, and the aircraft will have some transient response followed by a steady state constant velocity in which you will be moving forward, right? The input to the response have the temporal dependency here, right? So when you have such kind of a system, you can't treat every input as an independent of that, right? The previous state of the system as well as the current input affect the next state where the system can move on, right? For example, if you want to look at an activity, right, in a video data, if you are looking at a scene through camera where someone is performing an operation in an agriculture field, let's say plowing, right? So you are observing him from one point to another point, a sequence of data wherein we identify a farmer or identify a robot which is moving from one point to another point, and it's operational, right? It's a complete activity that we are trying to understand, right? That activity is a sequential data, right? Or sequence data, right? Its activity cannot be determined without that. For example, if you want to identify a gesture recognition, if a car is moving and you want to stop, right, you are giving a specific gesture to stop the car. That's a temporal activity, a person moving hand all the way to up and say stop, right? So till that activity is done, you cannot identify what is the signal that he is passing on to an autonomous vehicle, right? So these are sequential data which is very, very important when we are trying to predict. For example, if you wanted to operate a drone in a GPS denied environment, moment you say GPS denied environment, you are only using inertial measurement unit. IMU alone is not sufficient to predict the state of the system. You could have a recurrent neural network predicting the velocity based on whatever the observation that you have along with the current measurement, and that velocity is fused with the extended Kalman filter to get the states of the system. Then you have a way to handle it. Which velocity you are predicting? Predicting the velocity of the drone. Drone dynamics is important. The past state of the system and the current input influence the future state of the system. So those are the scenarios where recurrent neural networks will be used. Okay. So and another use case, if you want to look at it, you can look at it as stock market, or you want to look at weather data. You wanted to understand how the wind is going to be, right? If you are looking at a sequence of drones which is flying together, and you want them to fly without collision with each other, and each drone belongs to different operators, then you don't know their mission. So you may have to predict their trajectory such that you can plan your motion such that you don't collide with them, right. So in such scenarios, predicting the trajectory of other drones based on the data, that will come into recurrent neural network. It's something equivalent to say, I am going to look at the future stock price based on the current stock price, right. So that's all temporal dependent data. And here in the interesting aspect, if you look at why I am just highlighting the stock price and trajectory prediction of the drone, you don't know the dynamics of the drone which is flying. But what you have is observation, which is basically a velocity or distance, relative distance between you and him, right. You want to predict where he will be in the 3-dimensional plane next 3 seconds, right, based on the past observations only. You don't know the states of the drone, you don't know its dynamics, you don't know its control input. Based on the past data alone, you are trying to predict the trajectory, which is equivalent to stock market price prediction. I know the past data of the price of a particular stock. Can I predict what is the price in the future, right? This is the problem we are talking of, right. Now let's dive a little deeper to understand, right. Here we make certain important observations. The inputs that you are applying, it's not independent, right. That also is temporal in nature, right. The input output length is not going to be the same. When I say one specific sequence data, right, one sequence could be like 0 to 5 seconds. Some other sequence could be like 0 to 10 seconds. Let's say I want to learn to mimic like a pilot. I can have a different pilot. I can ask them to fly. I can capture the data. I can give a specific mission to them and then I ask them to fly. What I am trying to see? I am trying to see what's the kind of control input he gives for which how the system is responding, right. So I am learning his reaction to the states of the drone and his control input what he is applying. I am trying to mimic like a pilot, right. So some pilot may finish the mission in 30 minutes, somebody may take 20 minutes, somebody may take 40 minutes. So the data length is not going to be the same. But remember, the task is not changing, right. The mission is the same, okay. The sampling rates are same. Remember that, okay. The context might vary when he is flying to other, because based on the input that he apply, the response of the drone will be different, but the context in which they are flying might be different, okay. But we are trying to relate is input he is applying to the drone for a specific observation and reaching a particular mission, right. So there are interesting problems when we talk about sequence data. Why we are bringing not just only signal, we are also bringing in image. The course is all about perception, right. Moment I say perception, I am not only sensing the internal information, I am also sensing the external information, which means I am observing the extrinsic or the context in which the drone is flying. It could be a sudden wind and rain and snow, the scenarios can change, right. We are trying to understand the semantics of the environment, how the semantics are changing, and based on that we are reacting to it. Connecting to the problem of multiple drone flying, I am observing a specific drone in my video data and observing that it is moving at a specific distance from me. I want to predict what will be its trajectory such that will I have a collision with him or not, right, which means I need to continuously track this particular drone, find the relative distance in every frame. Using my past observation of relative distance, I need to identify where the drone will be in next 1 second or 3 seconds and see whether it is going to be in my path or can we declare there is a potential collision. If there is a potential collision, how we mitigate, right. Those are all coming under sequential data problem. Other classical thing is you talk about text. Text comes into that. Now, why I am bringing in language here, those students who are interested doing research later this course, they can look at how navigation models can be built based on language as an input. For example, whenever we give a mission, we describe them in specific words, right? Go to particular location XY, right? On the way, you just have to look for the targets. If you see a target, deliver, point of interest, deliver this particular packages, right? So now, how do we translate the sequence of words to a specific commands for the drone such that the mission can be completed with the textual description also comes into picture. There are a lot of interesting research you will see at the end of the course. We will try to show you how end-to-end navigations are gaining a lot of attention, where vision as an input when you are talking about navigation models, right. Now, let us dive a little deeper to understand. I am trying to get a data, right. I am currently observing a xt, right, t steps data, and I am calling that one sequence, right. That is the observation that I have. This is an ordered observation. It has a temporal correlation and dynamically changing measurement that we are getting, and its length need not be a constant based on whatever the mission that you are trying to perform. What we want from this data, we need to understand, maybe we can understand the trend, or whether there is a periodicity, whether there is a cyclic component being present. Why we need all of this? With all of this, we can predict what will be the future trajectory of this particular drone, or what will be the future action these objects which we identified in the image will be doing in the subsequent frames, right, in which direction it will be moving. That will be useful for visual surveying. If I see I wanted to track a particular object in my image plane, right, I detect him, and if I estimate he will be going in a northeast direction, right, with a velocity of v, then I can control my gimbal or even the drone in such a way that the particular object always remains in the center of the camera plane. Okay, those are the problem comes into picture. Okay, now let us try to understand the difference between a feed-forward neural network and a recurrent neural network, right. Foundation of shallow neural networks, when we talked about recurrent, basic multi-layer perceptron, radial basis functions and all this, right. If you look at all of them are called feed-forward neural network, when input goes from one layer to the next layer, right. There is no feeding back, there is no input comes back from the second layer to the first layer, right. And input is independent of the output. Okay, I am trying to predict the output from the input x. So, we are trying to approximate the relationship between y and x, right. There is no sequential relationship. Past input does not affect the current output. If you look at a recurrent neural network, the output depends on current input, right. The past, let us say if I am going to, this is a single perceptron, and if I want to show recurrence, what I can do is I can bring the past input back with a delay, could be unit delay, and feeding it back as one additional input, right. So, the input also come feeding it back, or I can also bring from output layer back to input layer with a delay, right. When you have any of these feedback connection, it is called recurrent neural network. So, if you want to understand clearly, you see here these are inputs to the network, okay, and you have hidden state, there are n hidden state, and one of them is considered as an output. All the hidden state fed back to the input layer with the delay, unit delay, right. This is a typical structure of recurrent neural network, right. Whereas if you look at a feedforward neural network, input goes to output, input goes to the next layer, input goes to the output layer, and so on and so forth. Okay. The feeding back brings in interesting challenge in learning, right. If you are trying to understand what is the difference between these two from the point of view of connections, connections between the neurons are single, forward directional, whereas if you look at a recurrent neural network, connections between the neurons are bidirectional, right. Not all neurons need to be bidirectional, some of them will be bidirectional. Feedforward neural network application perspective, if we ask, they are very well suited for approximating any nonlinear function to map the input-output relationship. On the other hand, if you look at recurrent neural network, they are suitable for system identification, control, sequence prediction, and those kind of problems, right. Now, from the perspective of learning, the complexity of learning in feedforward neural network will be very less, and there is no stability problem, right. On the other hand, because you have a feedback structure present in the network, the learning complexity is going to be high. There is a possibility of instability in the learning process, which means the network weights can grow unbounded. So feedforward neural network is a powerful tool for approximation, classification kind of thing. Whenever you want to have identification, control, right, trajectory prediction, recurrent neural networks are more suitable. I included one additional application called memory. See, recurrent neural network is suitable for a memory. For example, if I am giving an image which is partially corrupted, they will be able to regenerate the missing parts. So, storing data is easier to recover the original information from partial inputs, right. Recurrent networks, if I ask, right. So, I have various networks possible, right. So, I am just going to give you 4 different networks. First, we are going to start with very simple network called memory neuron networks. It is similar to feedforward structure, right. It has fixed associative memory. It can help you to capture the temporal relationship. Okay. The memory is addressable, stability is there, it can be useful for one step ahead predictions, right. Now, how we use the memory neuron networks make it more interesting. If you want to have multiple step ahead predictions, then you may have to use different architecture like a serial parallel model, parallel model. We will give a reading material. Those are beyond the scope of this particular course, but I will just touch base on one of such approach when we talk about application, but those who are interested can just look at the reading material to know more beyond one step prediction. Now, other we call typical recurrent network, where the hidden states are fed back to the previous layer, right. The problem comes is when you have a multiple such layer, vanishing gradient, the vanishing or exploding gradients comes into picture, back propagation through time becomes computationally intensive, and stability of learning becomes a bigger issue. On the other hand, if you look at LSTM, which we will also cover in subsequent lectures, how the cell state plus gates that learns to keep the hidden information and to predict the output is what is going to happen. Again, it is fundamentally sequential, suitable for sequential approximations and all that, and how we encode the state, how make them parallel, all this will be very interesting to look at it. On the other hand, you have vision data to be processed, right. Then you have an attention comes into picture, transformers and all that comes into picture. How they encode the visual sequential data and to approximate the temporal relationship is one such network possible, right. Now, this particular lecture will focus on simple memory neuron network. Okay. The architecture of memory neuron network is shown here. Whatever the white circle, it is called network neuron. Whatever in the red circle is called memory neuron. Okay. So, you see, for ease of understanding, I am showing a input layer, one hidden layer and one output layer. But like similar multi-layer perceptron, you can have more number of hidden layers. If you notice, the network neurons and input and hidden layer has only one memory neuron associated with that. Whereas in the output layer, each neuron can have more than one memory neurons. Okay. If you notice in the input layer, the memory neurons send the output to the next layer. There is no feedback connections between the memory neuron and the network neuron. Whereas if you look at an output layer, the memory neurons feeding back to the network neuron. Okay? So, that is an observation you should have. If I want to understand how exactly the memory neuron works, if you see here, whatever the input goes to the network neuron, you will get an output from the neuron, right. The output is scaled by the weight alpha and delayed by one time step, fed as an input, and memory neuron feeds its output delayed by one time step, but multiplied by 1 minus alpha, right. So, there is a feedback. So, this inherent associate memory structure capture the recurrence relationship very well here. Okay. If you want to understand more about memory neuron network, there is a interesting paper published by Professor Sastry. It is called Memory Neuron Network for Identification and Control of Dynamical System. We will share it in the reading materials for you. Okay. Now, if you look at, in a summarize, if I ought to say the architecture, each network neuron, right, each neuron has a memory neuron. Each network neuron has one memory neuron in the input layer and the hidden layer, whereas in the output layer it can have more than one memory neuron. These neuron captures the past relationship and captures the recurrence more effectively. Memory neuron takes its input from the corresponding network neuron and it also has self feedback, right. Each network neuron except those in the output layer has corresponding one memory neuron. The memory neuron in the output layer feed the output back into the network neuron. That is a structure you should understand, right. Now, for better understanding, I am zooming it further. You see here each network neuron feed, right, with the delay, unit delay. Okay. Here also there is a delay, okay, multiply by the weight alpha and passing to the memory. The output also delayed, multiply by 1 minus alpha, passing to the memory, right. Now, if I am trying to understand this in detail, I want to understand the dynamics of it. Let us say S11, the 1 corresponds to first network neuron in first layer, right. This is representing layer, this is representing the number, right. So, let us say S11 of k, k is a sampling instant where the output coming from the network neuron, which is nothing but g of x1 of k. G is nothing but your activation function, x1 of k is net input which is coming to the network neuron. Now, if you are trying to understand what is the output of memory neuron, V11 of k is the output coming from first memory neuron in the first layer, which is nothing but alpha 1 1 See, alpha 1 1 is nothing but the first memory neuron's weight in the first layer, right, into S11 of k minus 1 plus 1 minus alpha 1 1 V1 of k minus 1. So, this captures the recurrent relationship between the input and output. Very important point, the alpha is greater than 0, less than 1. Okay? Just think about it, if alpha is 0, right, then what will happen? This term is equal to 0, right, which means what? There is no information of current input going to the memory neuron at all, which is act more like a bias. Let us say if alpha equal to 1, this is a condition, right, alpha equal to 0. If I put alpha equal to 1, this term will be equal to 0. What does it mean? Whatever the current output of the neuron, delayed by one time step, and that is what your memory neuron is going to stay. If the alpha is between 0 to 1, the memory neuron captures the past information in exponential sense, right. So, if I try to expand this and say it might give, let us say this is the effect that I want to give, alpha being the effect for the k minus 1th step, for k minus 2 it might be lower and lower, 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 like this it captures, right. So, it takes the effect of past steps of input automatically, it depends on the alpha value, right. If alpha is 0.1 and 0.1 3 times, if you look at it, it becomes very small, right. So, it depends on the alpha value, it captures how many past n samples effect it captures inside, right. So, that is how memory neuron efficiently captures the recurrent relationship very well, right. Now, let us look at the output of the memory neuron, right. So, this particular layer I am just trying to highlight further, and to get you better understanding, W11 is the weight associated with the first network neuron to the memory neuron, F11 is the weight associated to first memory neuron to the first network neuron in the second layer, right. So, V11 is the corresponding output coming from the memory neuron. So, V11 of k we have defined, okay, and we have the weights of memory neurons are also defined here, which we explained in the previous slide, right. Now, let us look at the second neuron S211 of k. There are two input. For simplicity I have taken a two input system so that you can appreciate. S21, the second neuron in the first layer, which gets an input of x21 of k, and this is the output of the memory network neuron. Corresponding memory neuron V21 of k is alpha 21 S21 of k minus 1, one step ahead, one step behind, but plus 1 minus alpha into V21 of k minus 1. Here alpha 21 is a corresponding memory weight. Remember, all alphas are restricted between 0 to 1. Now, let us look at the first hidden neuron, right. We are interested in this, and we are interested in the network neuron, right. S11 of k is nothing but H11 of k, right. What is H11 of k? Is an activation function G. G is the activation function. You can use unipolar sigmoidal or bipolar sigmoidal, you can use any of the activation function. But if you look at this particular neuron receives input from network neuron as well as memory neuron, right. W11 S1 of k, W12 S21 of k. It also receives input from memory neurons F111 V1 of k, F12 V21 of k, right. So, sum of all the inputs is the net activation potential passed through an activation function which gives the output. Now, if I want to find out the output of this corresponding memory neuron, V11 of 2, first neuron in the hidden layer, the 2 represent the layer, okay. The 1 represent the neuron, memory neuron associated with the network neuron. Okay. It is same as the previous memory neuron, except they have a different weights. So, if you look at the last hidden neuron, there are M hidden neuron, right. This is the M neuron, right. HM2 of K, again function of network weight W M1 into S11, W M2 into S21, and this weight is F M1 into V11, and this weight is F M2 into V21 of K. So, basically I receive the sum of all the scaled inputs, and that is my activation potential. Passing through an activation function, I will get the output. The corresponding memory neuron is computed like this: alpha m to SM1 of k minus 1 plus 1 minus alpha m2 and VM1 of k minus 1. Right? Now, we saw how we are computing to the hidden layer. Now, let us look at how to compute the output layer. We have taken only one output neuron, let us say H1 3 corresponds to the third layer, only one neuron. We could have just simply say H of k, but I just continue the notation. Suppose in future if you are trying to do more layer, you need to do it appropriately. Remember, unlike other network neuron, it receives input from, this particular input is coming from network neurons, okay. In the previous layer, this input is coming from memory neuron in the previous layer, and the last two inputs are coming from the memory neurons in the same layer. Okay. That is why we see we written V11 of 3. Okay. Sum of all the inputs. So, basically this and this input plus this, and again we are computing this weights also, right. So, it receives inputs from network neurons in the layer 2, memory neurons in the layer 2, as well as memory neuron in the layer 3. That is why we have all the 3 terms comes into picture, and that becomes an activation potential. We take activation function G, and that is my output. Now, we know how to compute this particular memory neuron output V11 of 3, right, alpha 11 of 3, H1 of 3, k minus 1, basically from here it is coming, right, and 1 minus alpha 11 of 3, V11 of 3, k minus 1, right. This is V11 of 3, this is V12 of 3, right. Now, when I look at V12 of 3, it receives inputs from previous memory neuron. That is why instead of H, we are using V11 of 3 k minus 1 plus 1 minus alpha 12 of 3 V12 of 3 k minus 1. Okay. So, this subscript 2 represents the memory neuron number. Okay. This represent which network neuron it belongs to, right. The superscript represent the layer. Okay. Now, how do we train this network? Because it is a sequential data, what we use back propagation through time. So, we need to define the error function for all the k samples, right, and squared error we need to take and minimize for the entire sequence. Data here is one sequence, right. You will have multiple such sequence through which you will be learning it, right. I am just taking one sample at instant k to explain it so that it becomes easier. Okay. Different here, if you look at, unlike a normal recurrent neural network where the output from the previous layer or next layer fed back to the previous layer with the delay. Here the recurrence are present in local in nature, it is feeding back to the same neuron, right, and the alphas are restricted between 0 to 1 and hence the output coming from those neurons will not explode at all, right. By constraining the memory weights we can achieve the stability. Okay. Otherwise the computation of the gradient is similar to what we have done for multilayer perceptron. I am going to just take you through just to get the weight update, right, for the output neuron. Okay. One by one let us look at it. Let us look at the output neuron W11 of k plus 1, right. I want to compute this W11 of k minus, I am sorry, so W11 of k plus 1, right, minus eta time dou E by dou W11. So, if I am trying to differentiate the E with respect to W, so I will have the term 2, 1 by 2 into 2 S of k minus y of k minus 1 dou S of k by dou W1 of k. Here y is the true value, S is the predicted value. Dou S of k by dou W11 if I take, it is nothing but 1 time H11 of 3 k by W11 of 3, right. Remember S is nothing but H11 of 3. Remember H11 of 3 is nothing but activation function D times effect of network neuron in the previous layer plus memory neurons in the previous layer plus the corresponding network neurons. If I am differentiating H11 of 3 with respect to W11, all other term will become 0 except the first term, right. So, we will get a derivative of the activation function times S11 of 2k, right. So, if I am going to put it, right, it is nothing but W11 of k is eta times E13. I am just saying here it is not the cube, remember error in third layer, right. I am defining this as a error in third layer, that is what E11 of 3 error times input S11 of k. What is my error defined here? This is nothing but S of k minus y of k times the gradient of the activation function G prime. Okay. Similarly, I can compute gradient rule for F11, B11 and B12. When I look at this gradients, if you look at all of them will have a similar structure, learning rate times the error contribution times the input. Okay. We can also get the memory neuron output. Alpha 11 of 3 is alpha 11 of 3 k minus the corresponding feedback weight B11 of k, V11 of k into previous output minus the current, previous input minus current output. So, this difference will help my memory neuron to learn. After update, we just have to make sure clip the weights such that they are all between 0 to 1. Okay. if somebody wants to implement for n layers, right. So, how do we do it? Remember here alpha and beta corresponds to weights of memories, W and F corresponds, W corresponds to weight associating between two network neuron, F corresponds to weight associating with memory neuron to network neuron. Just for summaries, because there are a lot of notation involved, I thought I will just give a summarized input. NL is the number of neurons in the layer L, Zi nothing but the net input to the neuron, S whenever I say S, which is the output of the network neuron, whenever I say V, it is the output of the memory neuron. Sorry, there is an error here, it is neuron, Neuron, okay. W is the weight connecting ith network neuron in the Lth layer at the time k to the jth network neuron. Again, there is an error in all the neurons, okay. Alpha j is the weight connecting jth network neuron to Lth network neuron. Alpha ij is again connecting weight connecting memory neuron to the memory neuron itself. Beta j is the weight connecting memory neuron to the corresponding network neuron. Okay. So, last layer L, right, we just say that if there are L neurons are there, then beta Lj is the Lth memory neuron, right. Fj is the weight corresponding to memory neuron of the Lth layer to network neuron in the L plus 1th layer. Okay. Now, just to get summary, if I am just expanding beyond 2 input to multiple input, multiple layer, this is how we will do XL of k going from 0 to L minus 1. This corresponds to the network neuron, this corresponds to the memory neuron. We sum of all this, pass it through an activation function, get G. This can be computed for all the layer from 1 to L, right. Similarly, I can compute the output layer, output neuron, the last layer. I am computing all the contribution from network neuron in L minus 1th layer, right, and memory neuron from L minus 1th layer, the corresponding memory neuron of the Lth layer, that is my net activation potential. I will pass it through an activation function, get the output. The output neuron is always computed like this, Vj is alpha j into Sj plus 1 minus alpha j into Vj, corresponding one delayed input is what we need to take into picture. So, I can generalize this for L layers. Okay. Now, let us try to understand, I am keep saying temporal data representation. Let us try to understand what I mean temporal data representation from typical draw-yaw subsystem. If I can represent the yaw subsystem r dot, right, rate at which drone rotates in that plane, right, and omega d is corresponding the rate, right. So, if I am just looking at, and if I give a step input to the yaw stick, so I am looking at the drone to rotate, right. How do we capture the nature of the data, right? If I give a step input to the yaw stick, which means I am changing the thrust in forward and backward as well as left and right, so that yaw drone start rotating, right. What will happen is the yaw rate initially 0 start increasing and then it will become constant, right. Drone started spinning about its axis at the rate of 0.4 degree per second, or depends on the units that we are looking at, we may have to convert to radians or degree per second, right. Now, if I am breaking these responses, what we are seeing, I am giving an input u naught and I have an output y naught. When I am giving a u1, I am getting an output y1, right. So, similarly un to yn, it is a time, right. We are looking at what is the input at that time, what is the corresponding observation, right. But in a temporal data representation, when the second time comes into picture, the previous state of the system will influence the output y1, right. So, if I say there is no temporal dependency, u1, y1 are independent quantity, right. But actually in dynamical system, the y1 depends on not only the current input as well as the previous state of the system, right. We have to take care. So, typically if I want to represent in general form, x dot is equal to f of x comma u, right, where x is the state of the system, u is the input and y is the output, again is a function of g of x comma u, right. Let us say it is independent of input, then it will become g of x, right. So, if you see x is the state, previous state, how x changes with respect to u will be there and that will influence the next state with respect to time sense. So, this is a temporal connection that we are talking of, right. So, mathematically if I have to represent, my y is a function of u and h, right. It depends on the hidden state h. H is coming from the previous system, right. So, there is a famous theorem called Billings theorem. The Billings theorem says if the system is controllable and observable, then the output can be represented in terms of past k outputs as well as past k inputs. Okay. And we also have universal approximation theorem which says any such nonlinear function, if it is smooth and continuous, can be represented by a single hidden layer network with k hidden neuron, so that the relationship can be approximated to accuracy of epsilon, small epsilon number, right. So, that we can do. Now, I want to show you how we are going to apply for approximating the state of the system using memory neural network. Whatever the input that I am giving to drone, this basically the stick input, right, pitch or pitch and roll or yaw, right. So, and thrust. So, we have the data, right. So, which corresponds to change in thrust for, if we say quadcopter, it is a thrust in T1, T2, T3, T4, or if you are talking about hexacopter, octocopter or even a VTOL, right. So, your control input is what we are talking of. This is your actual system or 6 degree of freedom model, right. Whatever the output coming from the system is my y of k. I am delaying one step, passing to my input. I am also passing my control input to the network. Remember, the Billings theorem says I can approximate with the past input and past output. So, any of the memory neurons somehow capture the past recurrence dependency. This corresponds past recurrent dependency of control input. I am getting an output which is approximated y hat of k. The difference between them is an error which I will be using it passing through the network to update the weights, right. I can get the real time flying data, or I can use 6 degree of freedom model what I have implemented in MATLAB. I give a different input and collect the sequence data and store it and train the network. Test it with different sequence of input to see how well it is generalizing, right. So, you see here how well it is approximating the relationship between the data. It is very well capturing the dynamics accurately. One thing is when we do the simulation, we do not take care of the noise which could present in the system and disturbance that you can get in the external environment. Those are all not model when I am talking about it here. The real flight data will have all those effects into it, right. Now, how can I use this for GPS denied environment? Suppose let us say GPS signal is lost, or I am operating in indoor conditions or near the building or forest canopy or cluttered environment. So, what I can do, I can use IMU plus sensor fusion, right, or I can use with the terrain aided navigation, or I can use a SLAM, LiDAR and radar SLAM to estimate the velocity and pose of the drone and fuse it with the IMU to get the complete state, right. or I can use just IMU, integrate it and get the position velocity, but then I will have a drift over a time. That problem will come into picture. Or I can fuse it with magnetometer, barometer or optical flow. All of them can just give me an information. Magnetometer will give me the heading, barometer will give me the altitude, and optical flow will talk about the velocity, right. I can use that to fuse it and get the output. Or what I can do is I can also use memory neuron network to estimate the velocity based on the data and use that velocity as an input to my extended Kalman filter or uncentered Kalman filter to get the state of the system, which I will use it for control purposes, right. So what I did in whenever there is a map is not possible, localization is not possible, right, or I have just IMU alone, what we did here is we combine the drone data with memory neuron network. Whatever the observation I had, I pass to the network, estimate the velocity, and the velocity is fed back to my drone flight controller, which estimate the state of the system, and that I use it for control purposes, right. So one can use recurrent network to estimate the velocity and fuse it with external Kalman filter to get the state of the system, and that can be used inside your control logic. Thereby you can handle GPS denied operations. Okay. In summary, this particular lecture talks about what is recurrent networks, what is the difference between a feed forward and recurrent neural network. We talked about architecture of memory neuron network and backpropagation through time algorithm to update the weights of the network with a 2 input 1 output system, followed by generalization for general L layer network with N neurons, right. So we talked about all of that, and finally we talked about how one can use for system identification, right. This is the paper I am just referring to, right. If somebody wants to understand more than what we have shown in this particular lecture, suppose you wanted to predict for k step ahead, how do we use it, one can refer to this particular paper for more details and want to do further research and implement for GPS denied navigation. Thank you.